All right, so this video will have this question, which is basically verifying the solution to a differential equation. And then I will do a free answer question. Your new online 45-minute test claims it's only free answer questions. So I will do a free answer question, one that's a little on the difficult side, at least near the end, that's on differential equations. So this first problem, I mentioned this in the other video, that sometimes you can't solve the differential equation, but they want you to just verify a solution to it. So this is a good example of something like that. They give you the function y equals e to the 3x minus 5x plus 7. And they want to know this function is the solution to which one of these differential equations. Now, not that you can solve any of these. The only type we've solved were separable, and separable equations only have a first derivative in them. If you're curious, if you have a second derivative in it, it's actually called a second order differential equation, and second order differential equations are a lot harder to solve than separable equations. Once again, if you take a course in differential equations, they'll teach you how to solve something like this. These are solvable. It's sort of similar to the way you have a quadratic formula. You actually have a formula for second order differential equations that have second derivatives in them. But the bottom line is on the AP exam, there's no way you would know how to solve this, and you're not taught how to solve this by hand. So if you need to solve A and get with its answer, you would know how to do it. However, they gave you what the answer is. You just need to verify which one of these equations has that as its answer. So to verify it, you just need the equation where the second derivative minus whatever happens to the first derivative minus or plus this other number equals 0. Since we know how to find derivatives, we can get the first and second derivative of this and then plug them in and see which one works. So I'm going to find the first and second derivative, and I'm going to plug it into one that I know isn't the answer, and then I'll plug it in the one that is the answer so you can see how to solve it and what its solution is. All right. So which one of these works? I'm going to take this and get its first derivative. So the first derivative of this would be, remember this is a chain rule, e to the 3x's derivative is going to be e to the 3x, but we have to do the derivative of the inside, 3x, which is going to spit out a 3. So this thing's derivative is 3e to the 3x. This thing's, I'm still doing y's derivative, so I have to take the derivative of this, which is minus 5. And then the derivative of this will be 0. So y prime is 3e to the 3x minus 5. What's y double prime? Well, y double prime is the derivative of the derivative. Once again, if I'm going to do the derivative of this part, a chain rule is needed. The 3 comes along for the ride. I get e to the 3x's derivative is e to the 3x times 3. So I get another 3, which is 9e to the 3x. Derivative of negative 5 is 0. So I have the first and second derivative. Now I just need to verify which one of these would be the solution, or I should say which one of these is the original equation that this would be the solution for. So C is not the answer. I'll show you why it's not the answer. If you try to verify, if you go, well, let's take y double prime minus y prime minus 5. Well, if I do y double prime, which is this, so if I do y double prime, 9e to the 3x minus y prime, which is this, 3e to the 3x minus 5, make sure you put that in parentheses, minus another 5, I want to verify, does that equal 0? It's probably easy to see it doesn't, because 9e to the 3x minus 3e to the 3x isn't going to give you 0. It's going to give you 6e to the 3x. Now, I would have to distribute this negative, so I would get plus 5 minus 5, but the e to the 3x's don't cancel. So distributing this negative, I do get plus 5 minus 5. These cancel, but these don't. This turns out as 6e to the 3x. And 6e to the 3x is not equal to 0. So that's not a solution. So which one is the solution? Well, A works, and here's why A is the solution, because if I actually plug everything in, 9e to the 3x is the first part, so let's look at A. The second derivative would be 9e to the 3x minus 3y prime So that's minus 3 e to the 3x minus 5, in parentheses, make sure you group it, and then minus 15 at the end. I want to see if that equals 0. This time it'll work because I get 9 e to the 3x. Distribute this. Negative 3 times 3 is negative 9 e to the 3x. And negative 3 times negative 5 is plus 15. Now I got the minus 15. Now everything cancels. 9x to 9 e to the 3x minus 9 e to the 3x. That's 0. 15 minus 15 is also 0. So that one works. So basically the solution to this is A. So I wanted to show you this one simply because this is not solvable by you. You can't take this and go back and get the original solution. But knowing what the solution's supposed to be, you can verify it in the equations. And one of the things they like to test is, can you verify the solution? I showed it in the last couple videos on solving differential equations. I did verify some of the solutions. But here's one that you couldn't solve, where the only way to really know if it's the solution is to try it out in the equations, all right? And if you go on and take lots of math, you'll eventually figure out a way you can get this from these. But right now, you're basically working backwards and just verifying it, all right? One last thing. Problem. All right, sorry, I had to sort through some papers there. I promised you I'd do a real AP problem. So these are typically, now once again, your test is going to be a little different, so I'm not quite sure how they're going to handle it. But typically, this kind of problem is near the end. They usually put them somewhat chronologically in the way you learn them. So when I see them on AP exams, it's not uncommon for these to be one of the final problems. It isn't guaranteed. Also, I don't know what the new exam is necessarily going to look like yet. But if they follow the pattern they have followed, you'd probably see one of these, like I said, as one of the questions closer to the end. And typically they're non-calculator questions. So this is a non-calculator question. This was number 6, I believe, on an exam, probably something like 2015 or something. They asked something similar to this. All right. So they have you consider the differential equation, dy dx equals x times y minus 1 over 4. And so part A is get the slope field. All right. So to get the slope field, I'll just do like what I did in the last video. We just want to plug in the x and the y and calculate what happens. Now, since this thing is x times y minus 1 over 4, you might think, oh, you have to do a lot of calculations. There's 12 dots here. The good news is if you start, I'm going to start here with the zeros, all the x's that are 0. If x is 0 and you multiply it times the rest, well, the whole thing will come out as 0. So at 0, 0, x is 0, it'll make everything 0. So it's flat there. Make sure you kind of show it to somebody so they know it's there. Same thing at 1, because this is 0, 1. So since x is 0, it's going to multiply and 0 this whole thing out. So notice I'm not actually even plugging them in. I'm just reasoning it out. Same thing, 0, 2. And since the x is 0 all along this strip, they're all going to be 0 derivatives. Right? So this thing will calculate out to be 0 for every point along here. So since this thing calculates out to be 0, the slope is 0, and I'll put a flat line. Now, usually the way they break up the points is they'll give you a point for like one section and then another section. So I don't quite remember how they break this up, but this is probably worth 2 or 3 points on here. If I had to guess, this is probably worth 1 point, and then doing these is probably worth the second point. Because now I got to do a little bit of calculation, because now my x is 1. So if my x is 1, I don't really need to pay attention to it. I just need to see what y minus 1 is going to do. Well, here the y coordinate is 0. So if I plug 0 in here, I'm going to get negative 1 over 4. Negative 1/4 is going to have a kind of shallow negative slope. So just don't make it too steep. What happens when I go to 1? Well, 1 minus 1 is 0. So I'm going to get 1 here, 0 here. The whole thing says 0 out. I'm going to get another flat slope. What happens at 1, 2? Well, the y value is 2. So now 2 minus 1 is 1. I'm going to get a slope of 1/4. So make that kind of shallow going upward. And then if I plug in 1, 3, 3 minus 1 is 2. 2 over 4 is a half. So I'll make this just not quite 1, but a bit steeper than before. All right. Now, if I go over here, the x becomes -1. So all it does is negate all my answers from before. So since I have all my answers from before, over here, they should just be the negative version of everything I found. So since this was -1/4, it'll now be a +1/4. 0 will stay 0. +1/4 will be -1/4. And +1/2 will be -1/2. So if you draw something that looks like this, that's good enough. You get all your points. So that's the slope field. So they don't ask tons and tons of points. Here I've seen 8, 9, here's 12. They don't really ask too many more. All right. It's not really enough to get you what the function fully looks like, but they don't care. They just want to test to see if you know what you're doing. So this is enough for them to know you know what I just taught you about slope fields. Since an AP problem incorporates other things in it, this thing says, well, let y equal f of x be the particular solution to the differential equation. So whatever this thing solves out to be, they're letting this function be that solution. It has an initial condition given of f of 1 equals 3. They want you to write an equation for the tangent line to the graph of f at the point 1, 3. And then they want you to do a linear approximation with it. So let's focus on just getting the equation of the tangent line. Y equals f of x is whatever function is traced out by this. Its tangent line approximation, well, you have the tangent line at any spot because you found these slopes. The slope will basically be what the direction of the function is. It's also the direction of the tangent line at that spot. So if I want to find a tangent line, let me first write the equation of line. I'm going to use point slope form because that's easiest. Y minus y1 equals slope x minus x1. Now they gave me the point on the function. They want the spot 1, 3. The spot 1, 3 is here. So the function curves away, but at this spot, I actually know what the slope is and I know what the point is. I know what the point is because they gave it to me. You know, x is 1, y is 3. So if x is 1, and y is 3, I have almost all the parts of the line. I just need the slope. Well, I can get the slope because I have the differential equation. The slope at that spot, 1, 3, I calculate already, but I'll show it here. The slope at 1, 3, dy dx at the point 1, 3 is basically plugging in 1 for x and 3 for y. And that comes out as the one we don't need to worry about. 3 minus 1 is 2. 2 over 4 is 1/2. So the slope is 1/2. So this is the equation of the tangent line. Now they want me to use this tangent line to approximate what the function's value is at 1.4. Now at 1.4, I don't have any real information about where the function is. I could guess that it seems to bend up a little more. It's probably somewhere greater than 3. But if you want to do the tangent line approximation, this is the x value, using this to approximate what f of x is. So it's basically projecting this forward instead of using the curve. It gives me an approximation. What is f of 1.4? I don't know what it is, but using the line to approximate, I can just put this in. This is the x value. Plug this into the line and see what the line gives you. The line gives me, well, I'm going to plug in 1.4. and figure out the y coordinate is. So now that I plugged in 1.4, I can calculate y because the rest are numbers. 1.4 minus 1 is 0.4, and half of 0.4 is 0.2. So y minus 3 is 0.2. If I just add the 3 to both sides, I get y is 3.2. So this is what the tangent line says the function value is. That's if you took this spot, kind of folded over to 0.4, it would come out to be 3.2. The function itself probably curves a little more than the line. So the function is not actually 3.2, but the function would be close to 3.2. All right, so that answers the second part. Notice this uses information about tangent line approximations, which was from a while ago. And now for the tough part is here they want you to actually find that solution. What is that function y equals f of x? So I'm going to actually find, by solving the differential equation, what is that answer to this? What is the function that has this as its derivative with that initial condition 1, 3? So this one's a little tough because the math is a bit difficult on it, but we'll get through it. Hopefully you'll understand what I'm doing. This is a separable equation. I'm going to rewrite the equation. dy dx equals x times y minus 1 over 4. All right. It's separable because I can basically move this y term. I can divide it over, and I can multiply over this dx. And this 4, I can bring it over or leave it here. It's really up to you what you want to do with it. Let's divide over. If we divide both sides by y minus 1, we'll get 1 over y minus 1 dy. I'll bring over the dx to the other side. So if I bring over the dx to the other side, I still have the 1/4 over here. I have the x and the dx. So I'm not writing out all the work because it's going to take up too much space, but divide both sides by the y minus 1. There's that side divided, and multiply both sides by the dx. So I basically move the dx here and move the y minus 1 over here. Now I have this. It's separated, so now I can integrate it. When I integrate this, it's easy to get. This is going to be raised to the power 2. This is the power 1, so it's going to go up to power 2. When I divide by the power 2, it's going to double that bottom. So I'm going to get 1/8 x squared plus c. Now, when I take the antiderivative of this part, it's a little annoying because technically this is a u substitution. It's a function of a function. I have a y minus 1 in the bottom. Just to show it, it comes out the way you'd think it would. If you know the derivative of 1 over something is natural log. Basically, technically, you're supposed to do a u substitution. If you let u equal y minus 1 and du becomes dy, the replacement for the y minus 1 is integral of 1 over u du, because dy is du. 1 over u's antiderivative is ln absolute value of u, and normally it'd be plus c, but I already handled the plus c. And then what was the u was y minus 1. So it's natural log of absolute value of y minus 1. All right, so that's the antiderivative. So this thing's antiderivative is what we'd expect. It's natural log of y minus 1 absolute valued. So now I'm getting there. I need to find this plus c and get, they do want the y alone. So they do force me to get y alone. So to get y alone, I need to get rid of this natural log. What I'm going to do first is solve for the c. So if x is 1, then y is 3. So I can sort of figure out what's going on. So right now I get natural log of absolute value of 3 minus 1 equals 1/8 1 squared plus c. So this comes out, natural log of, well, absolute value 3 minus 1 is just 2. So this is ln2, not a nice number, equals 1/8 plus c. So c is actually a very strange quantity. So it makes this problem a little weird. C is ln2 minus 1/8. All right. So now I'm going to plug that back in and then work with it. The original equation now, because the y is positive, y is 3, 3 minus 1 was 2. It's the positive version of this. I actually don't need the absolute value bars because I'm dealing with, if I plug in this number or other y values around it, this thing is not going to come out negative. So I'm basically going to get rid of the absolute value bars here. Because this y is positive, I'm working with the positive version of this, because basically when I plug in this, it comes out positive, so there's no need for the absolute value bar. So I'm just going to ditch them, which is legal because of what I just said. So I have natural log of y minus 1 is equal to 1/8 x squared plus this weird thing. So plus ln2 minus 1/8. And once again, this is why this is kind of difficult, because you'd look at this and you'd probably think you were doing something wrong, but I assure you this is all correct. To get rid of this natural log, there's this little e down here. Remember, you can do that tornado thing from pre-calc and algebra 2. E to this power should equal this thing. So what is y minus 1? It's e to this whole big power. 1/8 x squared plus ln2 minus 1/8, all up in the power. And then this can actually simplify, but you don't have to simplify on the exam. So if I want to, just add the 1 over now, and my solution is I'm going to call this x squared over 8, just to make it a little smaller, plus ln2 minus 1/8 plus 1. Now the plus 1's not up in the power, it's by itself down there. Now this is the solution. I'll show you how they simplify it, but if I were you, once you get y alone, you're done. I wouldn't do any more, but just show you that this does kind of get a little better. This is y equals x over 8 minus 1/8, or sorry, x squared over 8 minus 1/8. These have a common denominator. I can make it e to the x squared minus 1 over 8 plus that ln2. And now that rule about adding powers, if I'm adding exponents, it's basically them multiplied with the common base. So this is the same as e to this part, x squared minus 1 over 8, times e to the ln2, all plus 1. So this thing, now the reason I was able to do this is because if you take things with a common base and you multiply them, you could add the powers. So I just reversed that. Since this had a certain base and I was adding the powers, I can write each one with e as its base multiplied. So I'm just reversing that addition rule about powers. From here, let's see if I can run out of paper. Good thing I have one below. E to the natural log cancels. So e and natural log are inverses of each other. This quantity is just 2. So the 2 drops out and becomes y equals this whole quantity, when they cancel, becomes 2. This quantity is e to the x squared minus 1 over 8 plus 1. This is the AP exam simplified version of the problem. So this is very difficult because I said, even when I was doing this, I did get this answer, but I went to check it because I was like, man, this looks really bad. And I thought I maybe made a mistake, but I couldn't find one. I went and it actually was the answer. So the math on this is pretty difficult. I wouldn't simplify if I were you. I would do anything possible to get to any answer. And I would leave the answer this way. And it looks like a hot mess, but it is what it is. So just realize, hopefully you can read this. This is e. All of this is in the exponent. And then this is plus 1 down, next to the e to the weird power. So a difficult problem. I think this section was worth 5 points in itself. Trying to think if I remember how the points worked out. I think it was, since it's 9, if this was 5, it'd probably be 2 and 2 for the other ones. So if I had to guess, this part would be 2. This was probably 1 point for the tangent line and 1 point for the approximation. And then this one, these differential equations usually have several points associated with them. There's usually many points for solving this. There's 1 for doing the separation. There's usually 1 for doing the antiderivatives. There'd be 1 for finding the plus c. And then in this case, probably 1 for getting the y by itself. I think I've only covered 4 points. There's probably a 5th point somewhere, maybe knowing to drop these absolute value bars or something. Or maybe using the tornado thing, whatever. I believe this worked out to be 5 points if I remember correctly. All right, so there's a real AP problem. This is a particularly difficult one due to this. Normally the solving the differential equations, you'll see in other problems, this is a hard version of it. They're normally not this bad for the solving. But this is a typical differential equation problem where it has a slope field, solving the differential equation, and then it has some kind of derivative thing with it. All right, so that ends this second video. Hopefully this made some kind of sense. Like I said, I don't see you on the other side, but feel free to message me with any questions or problems if they arise. All right, see you next time.